This video is going to go over empirical formula and molecular formula. So what you see here are two different molecules, nitrogen dioxide on the left with the blue nitrogen atom and two attached oxygen atoms, and then dinitrogen tetroxide N2O4 on the right. And so you'll notice the molecular formula listed under each one and the empirical formula listed under each one. And so it's probably clear to most of you that the molecular formula gives the total number of atoms of each kind of element, and the numbers are the subscripts next to the element type, right? So dinitrogen tetroxide has 2 atoms of nitrogen and 4 atoms of oxygen for every 1 molecule of dinitrogen tetroxide. The empirical formula for both of these molecules is the same, and so the empirical formula is sort of just the ratio of different types of atoms. And so for both of these, there is 1 atom of nitrogen for every 2 atoms of oxygen. And so you have the same empirical formula for these, whereas they have different molecular formulas. So we're going to do this practice problem. You have 3.407 grams of a compound that contains 0.605 grams of hydrogen and the rest nitrogen. We're going to determine the empirical formula, and then given the molecular weight, we're going to determine the molecular formula. After we do this, we're going to do one more involving mass percent and empirical formula. So it's a similar kind of problem, but if you're given analysis results but that includes mass percent, so for example here, a compound is analyzed and identified as containing carbon, hydrogen, and oxygen. The mass percents were determined to be 75.69% carbon and 8.80% hydrogen. Determine the empirical formula for this compound, and if the molar mass is 206 grams per mole, what is the molecular formula? So we're going to do both of these practice problems one at a time. But once we do these, we're going to use this sort of flow chart here. So we have a mass percent, and then we're going to assume a certain mass. 100 grams is the easiest assumption to make, and then we can assume a certain number of mass of each element, use the molecular weight to convert to moles, and then we'll figure out the mole ratio from that. So here we have our problem. 3.407 grams of a compound contains 0.605 grams of hydrogen and the rest nitrogen. Determine the empirical formula, and given the molecular weight, what is the molecular formula? So we know it has 0.605 grams of hydrogen, and then the rest is nitrogen, which means we can just subtract those two. The mass of nitrogen is the total mass minus the mass of hydrogen, and that gives you 2.802 grams of nitrogen. Now the empirical formula is the mole ratio. Okay, so these little x, n sub x, h sub y. X and y are going to be whole number values that represent the mole ratio of nitrogen and hydrogen. So how many hydrogens are there for every nitrogen, or how many nitrogens are there for every hydrogen? So it might be NH, it might be NH2, it might be NH3, might be N2H4, right? So we're trying to figure out, now N2H4 would be the molecular formula. The empirical formula for N2H4 would just be NH2. So the empirical formula is just the mole ratio. It's not the actual number of atoms. That would be the molecular formula, which we're going to do in part B. So we just need the smallest whole number ratio of nitrogen to hydrogen. So we need to determine x and y here. And those are the mole ratios. So we're going to take our mass of hydrogen and our mass of nitrogen. We're going to convert those using the atomic weights of both elements into moles. So we have 0.6 moles of hydrogen. We go to the periodic table, see the atomic mass of nitrogen is 14.01. Convert that into moles as well. Now you can probably see here that there are 3 times as many moles of hydrogen as there are nitrogen, right? So you can probably see that the ratio is 3 to 1. But if you can't see that, then you need to convert them somehow into integer, whole number integers. And so you're never going to write fractions like this. You're never going to write decimals. It's not in 0.200 h 0.600, right? You've never seen a formula like that before. Those need to be whole numbers. So you're not going to write it like that. You need integers. So you can see here that it's 3 to 1. But if you can't see it, the easiest way to convert them into integers is to take the smaller number, which is 0.2, and divide both of them by the smaller number. And what that's going to do is it's going to convert this 0.2 divided by 0.2 into a 1. And then the other one will be converted probably into a whole number. If not, we'll talk about what you do. So for the first one, you get 3 hydrogens for every 1 nitrogen, which means we end up with NH3. Now, sometimes, like here, it's telling you that sometimes the other one is really not is not an integer, it's not a whole number. It might be 1.5. And if that's the case, you have to multiply them all by 2 so that you convert them into smallest whole numbers possible. You might get 1.33, in which case you have to multiply it by 3 to get a whole number. We'll practice a few problems that are like that. So in this case, you get an H3. That's the answer to part A. We move on and do part B. The molecular weight is 34.07. What is the molecular formula? So here, you can just use trial and error to figure this out. If you know the molecular weight is 34.07 and you know the empirical formula, you could deduce that maybe the molecular formula is just in H3, or maybe it's in 2H6, or maybe it's in 3H9, or maybe it's in 4H12. You know that it breaks down into the smallest ratio of 1 nitrogen to 3 hydrogens. So you could just figure out what all the molecular weights are, and eventually you'll get to the correct one, which is 34. So if we do it that way, we write down all the possible ones that we can think of. But if you notice, these are all NH3 with multiplied by some integer value in. And if that's the case, and so one way, if that's the case, the sort of fastest way to do this would be to figure out what's called the formula weight, which is the molecular weight of the empirical formula. In this case, that would be 17.034. And then you take the molecular weight that's given and divide that by 17.034, and that'll give you this value n. So the formula weight times n is the molecular weight. So if we wanted to do trial and error, just figure out what all of them are, you could figure out pretty quickly that the 34 gram per mole molecular weight corresponds to N2H6. But if it seems like that's going to take you forever, then you could do it this other way. Take the molecular weight, 34.07, divide by the empirical, the formula weight, which is 17.03, and then that should give you the integer value 2. And then you know that you need to multiply NH3 by 2. You get N2H6. So this way you would have done 34.07 divided by 17.034. You get 2.00112474. That's about 2, which means that that's what that n value is. So the molecular formula is the formula unit, which is NH3, times 2, which still gives you N2H6. You need to write it out. You don't want to write it out this way with the parentheses and the little number 2 on the outside. You want to multiply that 2 through to get N2H6. You're not going to write NH3 in parentheses with the 2 on the outside. That's just not the way we write these formulas. All right, now we're going to move on and do this practice problem. We have a compound. We know the percent composition. We know it contains carbon, hydrogen, and oxygen. We have the percentages of carbon and the percent of hydrogen, which means we can calculate the percent of oxygen by just subtracting those two from 100. We get 15.51% oxygen. Now, we want to determine the empirical formula for this compound. Remember that empirical formula is the mole ratio. Now, one of the things here that sort of bothers people, this little flow chart shows you sort of the steps in how to do these problems. And this what I wrote here in black is sort of what most people are sort of disturbed by in these kinds of problems, is that you have to make an assumption that you have some quantity of compound, some total mass of your compound. Up here in the flow chart it says assume 100 grams of sample. The reason they suggest 100 is because you're given a percent by mass, which means that if you assume 100 grams total, then that means that you have 75.69 grams of carbon and 8.80 grams of hydrogen and 15.51 grams of oxygen. It's just easy. It's easiest for a percent to assume 100. So if we have 100 grams total, then these are the masses of the 3 elements that are present. And remember, we need mole ratio. The empirical formula will be CXHYOZ, and we need to figure out these numbers, what whole number integers go in these values. So we're going to convert grams to moles using the atomic weight. So carbon is here, 12.01 grams per mole, oxygen 16, and hydrogen 1.008. So we're going to divide by each atomic mass to get the moles. 6.3 moles of carbon, 8.73 moles of hydrogen, and 0.969 moles of oxygen. We're then going to take each of those three numbers. It isn't super obvious what the ratios are here, 6.3 and 8.7 and 0.969. Those aren't as obvious as they were in the last example with nitrogen and hydrogen. So here we're just going to take each of these numbers and divide by the lowest number, which is 0.969375. That's going to turn the last one into a 1. The first one is 6.50. Hydrogen, the ratio is 9, and oxygen gives you a 1 because you divided the same number by itself. Now, if you look at these three numbers, 9 is 9.00596 is close enough to 9 to assume that that's the integer 9. But 6.5 is sort of a half an integer, and so we can't write C6.5H9O1. We're going to have to multiply all three of these numbers by 2 to convert them all into integers. So we're going to do 6.5 times 2, and 9 times 2, and 1 times 2 to give us 13, 18, and 2. And that's going to be our final answer here, C13H18O2. That's the empirical formula. We know the molecular weight is 206 grams per mole. What is the molecular formula? So the molecular weight of this empirical formula is 206, and so the formula weight of this molecule is already the same as the molecular weight. So we know this is also the molecular formula as well. So that's the answer to part C as well. You get the same answer.